Thank you, and thank you to all the, as everyone has said, thank you to all the organizers. This is really a fantastic meeting. I haven't been to the KITP before, to one of these conferences, and it's been great. I would never have probably sat through a bunch of presentations on cloud modeling, and that was cool. That was really fun, so I'm glad to be here. I feel a little compelled now to try to have a pun at the beginning of my talk, since Corey had a pun, and I've been sitting here trying to think of one, and the only thing I can think of is we're at the end of the day, right? So everyone's getting a little tired. So I'm going to have, and we're going to be talking about mud aggregates or flocs. So I figured it's appropriate that we have a rather low density talk today. So we're going to have lots of pictures of images of low density particles. All right, that was my attempt. All right. Oh, I ought to. Before we get going, let me acknowledge my collaborators. And in particular, I want to acknowledge Ihsan Abulfazli and Ryan Osborne. They're both, one's a PhD student and the other one was a master's student in my group. And we're going to get in and we're going to look at two different studies that we've been involved with over the last couple of years. And they've each been the lead on those two studies. And then also as part of this project, kind of a larger project, Thomas Ashley, Kieran Dunn, and Jeff Nitrower are all also involved. Okay, so I'm going to be talking about muddy suspensions, and these suspensions are very dilute suspensions. And I'm interested in the movement of mud, how mud is transported in a turbulent flow, how it deposits to a bed, how it erodes. And I'm interested in these all the way from headwater creeks, all the way out to estuarine zone and coastal zones. And like part of our talk today will be on the Mississippi River. Part of it will be looking at some mud from headwater creeks, but I'm also interested in how mud moves out in the deep ocean in contorite boundary currents and how mud drifts build up on the bottom of the ocean. And I'm going to have a very general definition of mud and just say that it's particles, both organic and inorganic particles, that are on the bed in suspension that are less than about 100 microns in size. And these muddy suspensions, if you go in and you look at them, it turns out that they almost always exist in some form of state of aggregation. Okay, so it doesn't matter if you're in a headwater creek or you're out in the ocean, in the coastal zone or elsewhere. If you have these small particles, are almost always existing, at least some significant fraction, in an aggregate state. Okay. And one of the interesting things about these aggregates is that they can change in size and density. So the particles can get bigger or they can get smaller as part of the flocculation process that we call it. So in flocculation, you can have aggregation, which is particles coming together, they stick, and the aggregate then can grow in size, or it can break up. And so if we want to know the settling properties of any of these particles, the two sort of key things we need to know are the size of the sediment, some characteristic length scale or size, and we need to, it could be helpful to know something about the shape, but we need to know the density as well. So size and density are really important parameters for understanding where mud goes, how it's transported in a system, whether it deposits or transports out farther in the system. And for a grain of sand, you can pick up a grain of sand and you can measure it, you can know the size, you can know the density, and that's just what it is. But for mud, sort of the interesting thing is that its size distribution is dynamic. So it can grow in size, it can shrink in size. This can happen while it's up in suspension, it can happen while it's on the bed. And so size and density of the particles themselves then become a dynamic part of the problem. So if you're trying to model the transport of mud and say how it impacts the concentration of sediment in a river mouth plume or a turbidity current or your river, or how a floodplain evolves, or how sediment infills in a particular basin, you need to know the settling velocity, and to do that you'll have to know the size and the density of these little guys, and they can be quite dynamic. So some of the things that impact the size and the shape of these, the density, one of them is just the nature of the material itself. We think about like collisions or nature of the suspension, and we think about aggregation. It's going to be dictated by collisions and how easy it is for particles that get really close to each other to stick. And so things that matter are going to be like the concentration of sediment in some given volume. And it could be a number concentration, a volume concentration, a mass concentration, but some quantity of this sediment. The size is going to be important. And then some mechanism to bring them close together. So for example, my understanding is now after the last couple of days with rain droplets, you have coalescence and breakup, and what's important with driving the collision is different settling rates of the rain droplets, or the marine snow. It's the same thing. What drives collisions is variation in the settling rate of the particles. In a turbulent suspension, what really dictates the collision rate is the amount of turbulent energy that's there in the flow. And one of the ways that we characterize this in dealing with flocculation is with something called the shear rate, G, which I'm listing out just a few things here because we're going to look at plots, and we'll look at how things like size change as a function of these different parameters. So G is it's a measure of the turbulent energy or the turbulent scale. So it's, right, this eta here is the Kolmogorov microscale that's related to dissipation rate of turbulent kinetic energy, or you could think of it as 1 over the turbulent time scale. So that's G, and we use that as a quantification of the amount of turbulent energy, and it's going to be both a driver of aggregation because it's going to drive collisions, and then we also think of it as something that can break up a floc. So G has this dual purpose of causing aggregation, but it can also cause breakup. Other things that are important is the size of the sediment itself, the particle and mineral organic composition, and then we could think of dissolved substances in the fluid. So it might be different cation concentrations or different types of organic molecules that are in the dissolved phase here. They may influence the stickiness of the sediment. Okay, so these are some of the quantities that impact the size of these different aggregates, or the size and the density. And now if we say, well, what are ways in which people model this in the sediment transport world? There are really three ways, I think three primary ways people model it. So one is to say that in the end, what we want to know is how fast the sediment settles. So let's not worry about the exact size of all of these aggregates. Let's just say that the settling velocity of the suspension of this muddy fraction, the small particles, is going to be some function of these things that drive and dictate the size of the aggregates. So let's make the settling velocity a function of G, or the settling velocity a function of the concentration, or something like Delft 3D, which is a multi-layer, layer average model that we use a lot to look at morphologic development in coastal regions. This sets to include flocculation processes. What it does is it says that the settling velocity is a function of the salinity in the coastal zone. So that's one way in which we could do it. Another way in which we could do it is try to model the size. And it could be modeling a single size, some sort of average size of the particles in this distribution, or it could be trying to model the distribution itself. And like trying to model the distribution of the particles itself, the way that we do it is similar to the way that we model the size of droplets in a cloud. So I've learned a new technique here that I think we ought to try. It's the superparticle technique. So I don't know, maybe that will be another way that we can model the size of these sediments. And once you have the size, you can use some sort of settling velocity relationship that links the density and the size of the particle to get at the overall settling rate. And then a third way, which some of you in this room have done, is to model the particle interactions directly. Try to model the forces and resolve the flow around the particles, and add in some level of cohesion that would cause aggregation. Okay, I'm not going to talk about any of these models anymore. Instead, really what I'm going to do is show you kind of a sample of things that we've been doing. So I got into flocculation and working on this problem because someone, had done work on gravel bed rivers, and I got a new faculty job, and my colleague came and asked me, hey, I'm studying the transport of pollutants, and I think it has to do something with cohesive sediment, and I've heard flocculation is a thing. Do you think the sediment can flocculate? And I had no idea what flocculation was, and I'm like, oh yeah, let me just, I'll give you an answer here in a day or two. And I started looking into trying to understand the flocculation process, and I realized there's like a lot we don't know. And one of the things that I ran into initially was just there was some conflicting data in both the field and laboratory work about, like, we say flocs increase in size when salinity in the water column goes up, because the increased cations in the water shrink the electric double layer, allow particles to get closer to each other and overcome the resistant force and switch to an attractive force when they become close. And so salt is supposedly a massive driver of flocculation. And then there were a lot of field observations that said, there's not a lot of dependence with salt. And then there were some people saying, well, obviously the collision, the rate of collision is going to be dictated by the concentration of sediment in the water column. And then there was a bunch of data that was there saying, well, sometimes the flocs grow when the concentration goes up, and sometimes it doesn't, and we don't really know. And so there was all of these different models for predicting flocculation as well, but there wasn't a lot of good data to test those models or calibrate those models. So what we started to try to do is to run lab experiments where we made nice measurements of the particle size distribution in the lab, and we took time to vary parameters that we think could influence flocculation and vary those things one at a time, rather than having them co-vary. So like in the field, the turbulence, stress, and concentration almost always co-vary. Like in a tidal cycle, you're going to increase your stress, you increase the concentration. It's hard to disentangle those two things and look at them independently and build models. And so what we had started to do was to try to measure flocs as they exist in a suspension in the lab. And the way that we found to do this that seemed to work the best was with a camera system. So there are different ways to measure the size of small particles, which many of you know. Sort of one classic way is to use laser diffraction techniques. And you look at scattering of light from lasers. And usually you would run this through like a Malvern mastersizer or a Sequoia list instrument, and you could get a particle size distribution. But to do that, you always have to sample your suspension. And these flocs are quite dynamic and they can be very fragile. And so if you sample it, a lot of times you disrupt the nature of the particles as they existed here inside the settling column. So what we wanted to do was come up with a way to measure the size distribution in the suspension with turbulence. Because the other thing that would happen is people would measure the size of this material in very quiescent settings, which doesn't necessarily reflect a river or a high energetic estuarine zone. So we wanted to have there to be turbulence. We wanted to measure the growth and breakup of these things. And so we started using cameras. And cameras are great if you can get nice images, because you can collect a lot of data quickly and then use image processing to back out particle size distributions. So we did this in the lab. So I'll show you some lab data. One thing we can't do with all of this, and I'll put that as a caveat up front, is that we can't get the density of the material, but we can size material quite nicely while it's in a turbulent suspension, and we can do it at a rate that's fast enough that we get growth and breakup of these different of the flocs. Okay, so we did that. And we've been working in the lab, and then more recently what we've done is we've taken our lab camera and found a way to turn it into a field camera so that we can get nice in situ observations in rivers. So I'll show you some images from this, but what this is allowing us to do is to obtain in situ measurements of flocs in coastal zones and in rivers, creeks. And currently there's no instrument like this in the commercial world. So the closest thing to it is a list, and a list has some other limitations, but this is a nice camera system. And so what this does is you have a There's a microscope objective in here. We have a camera. We have a light source on this side, and there's a thin slit here that fluid, the suspension comes through, and we can image it using bright field illumination. And we can run this up to the surface where we have a boat, so it's powered and communicated over Ethernet cables. I'll show you some pictures in the next few slides. But this is allowing us to now, over the last, I guess, 2 years, really, to start to get nice measurements of these flocs as they exist in rivers, which is pretty cool. Okay, so we've been looking at a bunch of different questions, asking, right, how does the floc size distribution and settling properties respond to different drivers? So how do they respond to turbulence? How do they respond to suspended sediment concentration? What about deposition and resuspension cycles? As material deposits to the bed, let's say during a slack condition in an estuary and then is resuspended, what's the nature or the characteristics of the particle size distribution when it comes back up off the bed? How do organics, both natural and gums, which are natural, but they're sort of synthetic things we use in the lab, how do they impact flocculation? Do clay and silt-sized particles interact? How do we have what's going on with salinity when we change salinity? And then we've been making some field observations lately. So what I wanted to do was show you all these different questions, because one of our aims is to create this high quality data, and we use some of this data to test flocculation models that have been developed or make updates to them. But there's many of you in here who I think could do a better job than us in pushing forward the modeling front of flocculation. So we try to, when we collect data, we try to make it easy for other people to use. We're trying to build a big database of floc size distributions under all different conditions to help with testing and developing and calibrating models. So what I'm going to show you now is I'm going to show you a little bit of data from some time out on the Mississippi River, and then some things we've been doing to try to answer this question of, does salt even matter? So historically, people have thought that flocculation is very important in coastal zones where you have salt, but more and more people have come to realize that these flocs, they're aggregates, they exist everywhere. They're in freshwater rivers, they're in lakes, they're in the ocean as well. And so there's this question that sort of we had, as it was like, well, does the salt even matter then? If everything is already flocculated, does salt play any kind of role in modulating the size of the mud flocs? Okay, so observations from the field. I'll show you some observations from different places on the lower Mississippi River. These are freshwater reaches of the Mississippi River, and sort of three questions that we're asking here is, what's the flocculation state? Just asking the basic question of, is this stuff flocculated or not? There's a guy, Ian Dropo, who has been saying since the early 90s it's all flocculated, and he's the only guy who has been saying it's all flocculated. Most people have been saying, no, it really takes salt water to see if it's flocculated. So we wanted to just make measurements and say, what's the flocculation state? We're also interested in the spatial distribution. Since we have this instrument that can do profiles, we wanted to know how our floc size distributions distributed over the depth, how are they distributed left bank to right bank, and how are they distributed up and down river. And then we made measurements in the same location under similar discharges, similar suspended sediment concentrations, but one case was in winter and one was in summer, and so there is about a 20°C difference in the water temperature. And so we wanted to know, is there any seasonality to the size of the flocs? Okay, so we're going to look at two locations here. One of them is at the Bonnie Carey Spillway, which is upstream of New Orleans. So New Orleans is here, the Bonnie Carey Spillway, and then all the way down, this is Head of Passes down here, and then right up in here is we call it the Venice Main Channel, this right here. So I'm going to show measurements here. And in all of the data that we're looking at, there's no saltwater intrusion. So there is a salt wedge that can migrate far upstream here, start to come up all the way up to New Orleans. The data that I'm showing you, there's no saltwater intrusion. Okay, so here's the field camera. Here we are, we're deploying it off the side of the boat here. This is our schematic. We can drop it in to the Mississippi River, right, that's powered and communicated over Ethernet. We can go down a couple hundred feet, and we have a nice live feed of what's coming from the camera, so we can change the settings, we can adjust the position of the camera if we need to refocus it, and we can save images directly to hard drives. And so these are the types of images we get for scale. This is a millimeter. So this is an image from the Bonnie Carey spillway area. It's more energetic there, so you get sand up in suspension. So these are grains of sand, and then these are mud flocs. And so what we do is we collect these images at a high rate, and then we use image processing to come in here and extract the size. We do things like get rid of particles that are out of focus, and then we differentiate between sand and mud flocs so that we can get a fractionation of, okay, this is the sand size distribution, and this is the mud size distribution, and of course we have together the distribution with both of those combined. So we can profile, we can collect a lot of data. So here are sample images of the suspensions at our sort of two primary locations that we were comparing here, the Bonnie Carey spillway in the Venice main channel. One is during summer, one is during winter. So the top row is summer in both, the bottom row is winter in both. And sort of the first order takeaway is just that mud is all flocculated in the Mississippi River, regardless of summer or winter. From the images, I think you can see that the flocs are bigger here. So overall concentration is not that different between summer and winter, but especially here in the Venice main channel area, the flocs are much bigger during summer than they are during winter. All right, Matthew, this is for you. I wasn't going to talk about actual settling velocity values at all, but most flocs in the Mississippi River and most flocs in most places, I would say this is the order of settling velocity. So not getting up to centimeters per second, but something on this order here. All right, what about the vertical and lateral distribution of floc sizes? We have size populations at each of these points, but what I'm pointing right here is just the D50 of the floc size. And there can be a decent bit of scatter for the D50. Part of that depends on the number of particles that you sampled, and part of it could be just the nature of the suspension itself that you're sampling. So we're between 2,000 and 10,000 particles for each of these distributions. So we think they're fairly, this is a fairly good representation. We have a lot of profiles in the Mississippi River. These are just a few of them. I think one of the things that we were thinking was that there would be a strong trend in the particle size distribution from top to bottom in the river, and there really isn't. There's not. Occasionally you see larger flocs at the top and smaller flocs near the bed, which we thought would be reasonable because you would have higher shear near the bed, so you should break things up. But overall, it seems to be pretty well mixed, and we also have fairly consistent size statistics across the channel. So at a given station, one of the things we'd say is that it's kind of reasonable to use cross-sectionally averaged floc sizes. We saw bigger changes rather than going up and down in the water column. We saw larger changes going downriver. So as you move from the Bonnie Carey spillway, which is a more energetic area, downriver in both cases, downriver is moving this way, moving towards lower shear rates. You get larger flocs. There is a limit past which you go when settling starts to become a large issue, and then your particle sizes drop as your shear rate goes down because you get more and more settling. But in this region of the Mississippi where we're at, as you decrease the shear rate, you increased floc size some. So we had an increase in floc size moving from the Bonnie Carey spillway down to Venice main channel. So that we did see that, and that was a consistent trend. However, the biggest difference we saw was just going between summer and winter. So the red dots here are the summer floc sizes on the vertical axis. Shear rate is down here on the horizontal. All of these are lower than the Kolmogorov micro length scale, so Kolmogorov would probably be somewhere around in here, and these are D50s. Okay, so what we think is going on, we looked and thought, well, maybe there's some difference in the salts, but there's no difference in the types of cations that are there or the concentration. There's no difference in the dissolved organic content. That's all the same concentrations. The Mississippi doesn't have a lot of seasonality in that, but there is a big difference in temperature. And so what we think, based on data that other people have done in looking at the activity of particle-attached microorganisms, is that as temperature goes up, you get more activity of the microorganisms that are bound to the particles, and you also have a higher chance for algal blooms, and both of those things are going to produce organic binders that help to promote flocculation. So we think temperature is a type of proxy for a particular type of organic that stimulates flocculation. All right, observations from the lab. I will go through this part here pretty quick because I think we're nearly out of time. So one of our big questions here was, okay, well, if the flocs if the Mississippi mud is flocculated, does salt even matter then? So and we can think of it from two perspectives. One, as the Mississippi River hits the salt water, either in the saltwater intrusion that's there in the vertical or laterally as it goes out into the Gulf, is there going to be a change in the state of the flocs as you hit salt water? And this is important for thinking about even engineering applications, such as if you have diversions in the Mississippi River, they're considering putting in diversion structures that allow water with sediment laden to go out into the bays with the hope of that sediment settling out and creating land. And so, like, one of our questions is the salt, the increased salinity in the bays, how is that going to impact flocculation? We also had, this is a interest in, like, in the East Coast, the United States, in the Midwest, we put salt on our roadways to melt the ice, keep the roads safe. And that salt eventually makes its way into our creeks. And so I was really interested in whether or not that salt has any impact on the transport characteristics of the mud, because it could be something that impairs our streams. So we did an experiment where we took natural mud, and we looked at putting different types of roadway salts with this natural mud from a stream, local stream, and seeing how does the roadway salt impact the floc size distribution at specific conductivity levels that have been measured in local streams after winter storm events. So after they put de-icing road salt on the roadways, and then we have snowfall, eventually that melts and makes its way into the creeks. It ends up bringing up the salinity in the stream to something like 0.2 PSU to 0.3 PSU, which is not a lot, but it's definitely there. And one of the things we found was that it actually can make a really big difference. That this is the natural mud here in DI water. This is natural mud in an undisturbed stream. So we went to a stream and collected stream water where it had not been impacted by the nature of where it's at. There's no roadway feeding into it, and collected stream water there. And you do get flocs just from the organic binders that are there, but it has a pretty low ion concentration. And so most of the mud stays in an unflocculated state. But then as soon as you add just a little bit of these roadway salts, what you do is you start to form more salts. And it's hard to see. It's hard to see here. There's the tiny particles. You can't see the tiny particles. But what happens is that all the tiny particles start to get trapped inside the floc, and that becomes a big function of the salt. Yep. Okay, and it has an impact on the settling of this stuff as well. So the salt type, even if you have natural mud with organic, salt still does make a difference. And so that is an observation that we found from the lab here. So we had a question from the field. We came back to the lab and worked on answering that. Okay, and then we've looked into more detail as to how does salt impact the size distribution of the flocs with and without natural organic binders. And if you're interested in that, you can talk to me afterwards because I'm out of time. So I'm going to stop there. Let's see, a couple of things to highlight here. These aggregates are everywhere in natural streams. Organic binders, this is something that we've noticed, that organic binders are really necessary to get to floc sizes over 100 microns in size. So if you have flocs over 100 microns in size, it's likely because of organic binders. One of the things that salt does is that it doesn't necessarily change your overall largest size of your floc, but what it does is move more of your material from an unflocculated state to a flocculated state. And so it tends to shift the particle size distribution from one that's bimodal to one that's unimodal. And it definitely, in doing so, it definitely increases the overall settling rate of the suspension. Okay, I'll stop there.
Thank you very much.
Mm-hmm.
Okay.
Hi, amazing talk. So I wanted to ask, how much of mud, like debris, is responsible in formation of marine snow, for example? If you go deep in the oceans, where does the effect of mud flocculation
turn to
doesn't really matter in formation of marine snow, for example?
Oh.
And also in your field data, since you're in a natural setting, how much of your aggregates are biotic and how much of it is abiotic?
So I can tell you how much organic material we have in the mud based on just loss on ignition. So we'll take our mud samples and then we'll burn off the organics, and the organics are about 10%. I think the organics are really important in the binding, but they have both mineral. There'll be solid silt particles in there, there's clay particles, then there's cells, like in marine snow, and there's also other products, like organic products. If there's no sediment there, then marine snow, the way that I'm understanding it, is going to be cells, right? And so it's just a matter of, is the sediment there? I think from plumes, you probably can get, especially on the far edges, some combination of the two, right? You get things that are sediment particles also coming out of plumes, but there are perhaps already some marine snow aggregates, and there's a joining up of those two things, but I haven't measured those. I think in the deep ocean, where flocculation is more important is where you have in boundary currents, where you have mud drifts that are building up. I think mud flocculation is important there, maybe more so than the marine snow. But it's just I don't know how much mud is there in the water column.
Hi, cool talk. I was wondering about the formation of the flocs, and you said they can form right on the bed, or they also can form dynamically in the water. And
yes.
How important is it whether they formed on the bed and were eroded as flocs or formed in the water column? And can you measure
which
that?
one? Yeah. So that's a good question. We tried to run some experiments where we created flocs on the bed by having really low shear, so material settled out and then sort of rolls around in the bottom of our tank, and you see the growth of, you get some really, really big, low density, cohesionless-like aggregates or grains moving around on the bed. And in our experiments, when we pulled them back up, when we resuspended them, they actually quickly broke up and went back to being the size of the particles that were in the water column before they deposited. So they grew immensely on the bed, but they were fragile enough that when they were brought back up in suspension, they broke down to an equilibrium size very quickly. I don't know if that was a specific outcome of our experimental apparatus. It's I think if you had something that was more consolidated and compacted and you had a rip-up clast, I think that would show up as an aggregate of a higher density. But I have no way of distinguishing in the water column where the floc came from. But it's a good question.
Thanks.
Yeah, thanks for the nice talk. I maybe have missed it, but
do you have information on what the surface charge or the zeta potential of the materials is?
Not these materials. So we have done a few experiments on like measuring zeta potential under different conditions. And there was a whole line of reasoning that you're trying to use zeta potential as the primary thing to talk about the suspension stability and whether or not it's stable or unstable, aggregate or non-aggregate, from the environmental engineering and chemical engineering.
My point is just that if the surface isn't significantly charged, then the screening of salt won't have an effect.
Yeah.
Because it has to have a reason to accumulate.
Yeah. So we have not done many measurements with zeta potential, or haven't used that. There was a big push to use that as some way to talk about stability, right? And added coagulant, and can we use this to help predict floc size? And it never really materialized into anything predictive. So we stopped making the measurements.
Well, I had a separate question was, so mixed road salts then are what? Are they a mix of sodium chloride and like calcium chloride?
Yeah, and magnesium.
So you have a significant component of divalent.
Yes,
salt.
the divalent they're very powerful.
Much more powerful.
They're much more powerful. Yeah.
Okay, thank you.
Yeah, and so they are like super flocculants. Yeah. And another thing, in addition to that then, is there's a lot of experiments that people have done using table salt as their flocculant, but sea salt is actually far more potent because of the, so you need to, if you're going to do this and make it relatable to salinity, you have to use sea salt. You can't just use table salt. Yeah.
Hey, just a quick question. So you demonstrated the importance of, in fact, the concurrent effect of salt and organic.
Yeah.
So do you have any plan to actually measure organic, like in one of the field, I think the summer floc is much bigger, you suspect it's organic.
Yeah.
But I think there are people like estimating EPS.
Yes.
I think any plan to,
we would
comment on that?
Yes. So the comment is initially we set out and we were kind of naive and we were trying to measure dissolved organic carbon without any differentiation of what type of organic it was and doing loss on ignition. And those are kind of meaningless. So extracting EPS is quite hard. So we've tried a few times using some methods. And then we've tried to look at the sort of the weight of the different organics to say, is it EPS or is it a more of a humic substance? Because the humic substance will be less sticky than the EPS. And we would like to do more of that, but nothing we have done yet has given us good data. So we're probably just very poor at doing these methods. But the hope would be, that you could quantify not just the amount of particulate or dissolved, but also what type of organic it is. But there's no standard way to do that, and we've failed in all of our attempts to do it.
All right, well, thank you, great talk. First of all, I want to thank you for your mud flocculation database. It has really helped us a lot in the modeling validation that we've been doing with Eckhard and Tom. And then I just want to share my experience when it comes to adding salt.
Yeah.
If you just think about flocculation in terms of does it flocculate or not, then really the amount of salt is incredibly small. Even it doesn't depend. So it's really, regardless of whether you're looking at kaolinite or bentonite, the critical salt concentration for the onset of flocculation is usually below the salinity that you find in open water bodies anyway.
Yes.
So that's my experience.
I 100% agree with you. Yeah,
right.
Yeah.
And then when you're in addition, and so now I'm coming to the question, because I'm basically just confirming what you said, which is great. Have you any means when it comes to adding organic contents? Because I think that would also change the density of your flux.
Yeah.
And so do you have any means or any plans to measure porosity or perhaps even permeability of the porous aggregates that form?
I would like to do that. So we'll do things like measure settling velocity and back out some rough effective density. But those measurements are quite hard to do on these for various reasons. I've thought about trying to somehow freeze them in epoxy or something and pull them out and do some more quantitative work on them in terms of like measuring the structure, but I haven't done that. So there is a group in the UK that has done that. Yeah, so that's the best that I've seen on anyone trying to quantify those. So all I've done is measured settling velocity, and I've measured size, and I try to back out some effective density.
Okay, well, maybe just as a bit of an encouragement,
Yeah,
I think this would be
try.
super valuable. Yeah.
Yeah.
Thank you.
Okay.
So very nice talk, thank you. So technologically, flocculation is very often coupled to flotation. So introducing bubbles into the flow. And so so these rivers, there's no air entrainment, I guess. There's very little bubbles because it will influence the flocculation a lot.
I have never ever thought about.
So the water treatment plants is flocculation and flotation. Washing out iron ore, you have huge machines that do flocculation, and as far as I know, I was once on a proposal that didn't get funded. I had no idea about the topic, but they taught me about flocculation and flotation and these huge gigantic things that they use to clean out iron ore. And it turns out there's a lot of open questions that are completely not understood. It's because it's the action of turbulence with the bubbles, and then also with surface tension and flocculation, right? Which then puts the stuff on top of the water, right? So, but you didn't see any effect, right? So these rivers have very little bubbles, I guess.
No, very little bubbles, especially something like the Mississippi. There's very little.
It's very quiet.
It's the free surface is very quiet. I mean, there's dissolved oxygen. That's a function of temperature, but there's not. I wouldn't say there's.
It's only when you go into the sea and you get sea breaks.
You maybe have bubbles from ships passing through, but I've never thought about the bubbles.
You've seen any effect, Okay, thank you.
But there could be. I don't. Yeah.
There could be exchange with swamp areas where there is significant gas, isn't there? Where you have rotting material.
There could be. So I've never thought about the bubbles. There could be decomposing material, not even in the swamp, but in the river itself. There's organic material on the bed. It could be decomposing. I mean, it's not like you see tons of bubbles, but it may have some influence.
Yeah, I'm impressed by your work, both the field and the lab. So the traditional explanation for the formation of deltas is that as it meets the sea, the fluctuates and then the particles fall down. So you're basically shattering that explanation. But you did mention one thing, which you talked about mixing and turbulence, and I've seen some people present data to the effect that turbulence, in the spirit of the first day of the conference where we're talking about caustics, that there's a possibility. So is there a possibility the particles would actually aggregate as a result of higher turbulence? I've seen data presented to that effect, and I wondered if you care to talk about that.
Yeah. So the first thing I would. So with formation of deltas, there's also just a lot. So sands and gravel, you can get a formation of a delta with sands and gravels without flocculation. So I think what's different is that you do see a lot of accumulation of mud in estuarine zones, and it could be salt, but it's very likely just a hydrodynamic effect. And actually, one of our collaborators is working on kind of that component to show that it's more of a hydrodynamic effect in terms of why you get a large accumulation of mud in estuaries. But the second question with turbulence, so the only way that I've really thought about turbulence is as a means of bringing particles close together and as a means of breaking up large flocs. And so certainly it enhances it enhances the collision rate under higher turbulence. And so you see like the growth of the flocs is faster under higher shearing rates. But then the floc size is also, the ultimate size is also lower. So they grow faster, they can be denser, the particles are denser, but then the ultimate size is lower. One of the things you see if you're like making measurements in the field in an estuary or even in our tank is that there is an optimum, if there is a turbulent shear rate for which you will observe the largest particles in the water column. And the reason for that is that as you keep dropping the shear rate, the resuspending forces are going down. So you start to settle out your big particles. It would seem that if you could just keep things in suspension forever, that the lower the shear rate, you should get bigger and bigger particles. The idea with, so there's, as I'm the first day, thinking about the first day and the idea of like, there could be zones of preferential concentration where concentration is higher and you have more chance for collision based on particles being probably, my understanding is right around Stokes number 1. Is that where you would get particles on the outside of an eddy, like congregating? Is that correct? Yeah, so there's a chance that you could have preferential concentration around there. I think most of the time our Stokes numbers are going to be on the order of like a tenth, like 0.1, 0.2. For really energetic systems and big flocs that are really bound together with organics, you can start to approach that Stokes number of 1. But for the most part, we're quite a bit lower than that. So then I'm thinking, well, maybe that's not such a big, maybe you don't get preferential concentration on the edge of the eddies, but I don't know. I have no idea. It would be really cool if that effect is there.
Okay. More question? No? Thanks.
Thank you.
A lot, Kyle. Okay. I would like to thank all the speakers and also the audience for making this session so lively.